Hi everybody, so my name is Paul Boniol, and today I will present you our work on an extensive evaluation of model selection for time series anomaly detection using time series classification methods. So this is a joint work in collaboration with Emmanuel Silviardos, John Paparizos, Panos Traanias, and Temis Palpanas. So all this work is about anomaly detection in time series. So anomaly detection in time series is a very important problem where the objective is to identify points or subsequences within a time series that might correspond to unusual or potentially harmful events. So this topic has been studied actively in the last 20 years. And in the two past years, several benchmarks have been proposed with large collections of labeled time series. And in these benchmarks, the overall conclusion is that there is no unique method that work on all specific types of time series. So when you have a use case, when you need an anomaly detection methods for very heterogeneous time series, then it will not work. So here in this figure, we can see that the best approach is a different one based on the different types and characteristics of the time series. So a possible solution here is to actually use either ensembling or model selection. So ensembling is something also very well studied, and one very basic idea of ensembling could be, for instance, to run all the detectors and compute the average anomaly score and use it as a final anomaly score to detect the anomaly. So doing that is already improving the accuracy. So here we see the results of several anomaly detection methods on the TSB-UAD benchmark. And we see that when you apply the average ensembling technique on these detectors and on TSB, we observe an improvement in terms of accuracy. But the problem is you have to run all the different anomaly detection methods. And this is very significant in terms of execution time. So this is problematic. So a second solution is to use model selection. So in model selection, the idea is to actually train a method to select in advance, based on the characteristics of the time series, one detector that should work the best, and then to use this detector to compute the anomaly score, and only this one. And in such case, the execution time is very slow compared to the ensembling approach. So let's imagine that we have at our disposal the perfect model selection approach that always selects the perfect detector for each time series. The results would be here in white. So in white, so we call it Oracle. And we see that the improvements compared to the individual detector and the average of something is significant, that 3 times or even 4 times higher. So this is very motivating to actually try to build and to evaluate model selection techniques. So we know that this selection could be performed with time series classification algorithms, which is a topic very well studied also with a lot of different methods proposed in the literature. So the question is, are the existing methods for time series classification working when used as model selection approach for anomaly detection? So where are we in this graph, both in terms of accuracy and execution time? So in this paper, we try to address 3 main questions. The first one is to know what is the best. So are the individual detectors better, the average ensembling, or the model selection approach using time series classification? Then we also want to answer the question of what is the best type of input for this task. So is it using features extracted from the time series or using the raw values of the time series? So each individual points or subsequences. And then we also want to know in the scenario that you have like some specific type of data for the training and something completely different for the testing. So are the model selection approach trained on some data and test on some very different data still working? So these 3 questions, we will try to answer them in our experimental evaluation. So in order to do that, we need to build a pipeline, so an experimental pipeline. And the first step, the first thing we need is labeled time series. So we need like time series for which we know which detector is the best to use. So in order to get this time series, we use the TSB-UAD benchmark that contains close to 2000 time series. And we know in advance because the best methods among 12 detectors. So we can use it as the classes, the detectors, and as the labels for each time series. So the second step is about segmentation, and this step is pretty important because in the case of TSB UAD, but in the general case of time series, the time series are not the same length, and it's better to deal with equal length methods, and this is better to actually make the time series equal length. So in order to do that, we will segment the time series into equal length subsequences, non-overlapping subsequences, and we will assign the same label to all these subsequences belonging to the same time series. Okay. So the third step is to actually make the prediction, to select, then to predict which detector is working the best on each of these subsequences. So to do that, this is where time series classification approach are involved, and we can test many different approaches. So approaches that work on features. So we need to extract features using TS-Fresh, for instance, and perform the classification on these features. We can also work on the raw values directly. So we can use Rocket, one of the state-of-the-art time series classification approaches, but also deep learning-based approaches. So we have like convolutional-based approach, ConvNet, ResNet, insertion time, and some transformer-based approach that have been proposed also in the literature. So then we can compute a probability, and then one detector. We can predict which detector is working the best for each of these subsequences, but then we need to get only one detector for the entire time series. And in order to do that, we will do a majority voting here to actually get the one that has been the most selected and run this detector on the input time series and get the anomaly score. So this is the entire pipeline. And what we will evaluate here are the time series classification method in the C box here, and also the importance of the window length here. So we will conduct our experimental evaluation on the TSB UAD benchmark, so 2000 time series from different domains. And we will measure, we'll compare 16 time series classification methods from different domains, so the one we listed before. We will use TS-Fresh to and minimal features using TS-Fresh for the feature-based approach. And we will also apply them on 8 different segmentation lengths from 16 to 1024. And we will actually get the values. Each of these classification methods will be combined with one of the lengths. So we'll compute all the possible combination between the two. So we will do a random split of 70% of the TSB UAD benchmark for the training and 30% for the test. So this is an important point, and we will come back to this at the end. So the overall results are here. So here we see the performances of the models with the most adequate segmentation length. And we see very interesting things here. So in terms of accuracy, we observe that our raw values methods are better than features-based approaches. Okay, so we see it here. We also see that convolutional and transformer approaches are quite equivalent in terms of accuracy, and that all these model selection approach are better than the average ensembling and the individual detectors. We also see that in terms of execution time, the ensembling approach is very slow, and the model selection approach are in the same order of magnitude as the detectors, the individual detectors. So we can also try to evaluate the influence of the window length. So here we see the average performances of each type of method, or each family, when we vary the window length. And here we see that this impact is quite different between the different families. So we see, for instance, that transformers are not working well with small window lengths, and we need big window lengths to get good performance with the transformer-based approach. We see that for feature-based and for convolutional-based, the impact is less significant in terms of accuracy, but in terms of execution time also, so this selection time, so in order to make a prediction, we observe also big differences here. The transformers are very slow for the for small window lengths. This is correct because we need to do way more prediction for each of the small subsequences for one time series, and then to merge them. So it is slower to actually use small window lengths. Then we can summarize this entire experimental evaluation here. So here we see the plot I showed you during the introduction. And we see that the average ensemble method is here, still better than the individual approach. But the best model selection approach that we succeed to train is here, right in the middle between the average ensembling and the oracle. So this is very, very good performances, even more when you look at the execution time, because the execution time is within the interval, the execution time interval between the slowest and the fastest vectors here. But also what is quite motivating here is that there is still a very large margin of improvement. And this is very motivating for further research in this direction, trying to improve maybe the selection, but we will discuss also the perspective later. So the final question that we need to address is the case of out of distribution. So I said in the first experimental evaluation, so in the previous slides, that we tested doing a random sampling of 70% for the train and 30% for the test on the entire TSV. But in this case, the data in the test and in the train are from the same domains. So in a way, the time the model selection approach already seen the different types, all the different possible types of time series in the train and in the test. But now the question is it still working when we remove one specific type of time series, so one data set, the benchmark, and keep it exclusively for the test? So here what we can do, for instance, is to look at one specific benchmark, and we will use all the time series -1 for the training and keep the last one for the test. So in this case, the data that on which the model selection approach will be evaluated are very different and very unique, and we will be able to evaluate how model selection approach can transfer to these new types of time series. So we can do it multiple times and actually do all the combinations, so one versus all, and compute the results. And what we see here, so we see the accuracy on the y-axis of the different type of approaches. So here we kept only the best of each family. And we see that the performances are really different based on the fact that we removed either one dataset or another. So here, for instance, when we remove occupancy and only use it for the test, so this is the performance on occupancy, the results are pretty good, better than the best AD selected on the train, which means that you compute on the train, you select the best AD, and then you run it on the test. But this is not the case for all the datasets. So when we look on average the results, we see conclusions that are completely different. This time, it is way safer to use the average ensembling technique. And we see that even though the convolutional based and the ResNet method are better than using a single detector, they are worse than doing the average ensembling technique. And we see that the transformer are this time pretty bad and pretty close to only using one detector and the one that performs best on the train. So this is very interesting conclusion here, saying that when you have very new data, it is way safer to do ensembling rather than model selection. And this is also very motivating in terms of conclusion and perspective, because in such cases, there is a large margin of improvement in the out of distribution scenario. So to conclude quickly, we measured that in the general case, when you have like a uniform in terms of origin and type of time series, the model selection approach are better than the individual detectors and the averages, significantly better. We also measure that raw values based time series are better than feature based anomaly detection model selection approaches. And then we also measure that observe that the average ensembling technique is significantly better in scenario in out of distribution scenario when you have unusual and new type of time series. And in terms of perspective here, we can see that maybe we could work on the rank. That we know we have this rank information. So which method is the second best, and maybe we can use it in the train to actually get better results. We can also use the execution time within the train to actually get the best trade-off between accuracy and execution time. So these two are two possible improvements and future directions to work on. So thank you very much for your attention. And if you have any question, feel free to contact me. Thank you very much.